Hi, everybody. Welcome back to this week's Born Symposium. I'm going to pass it right away to the moderators, Anna, Abby, and Alessandro. It's your show.
Thank you. So I'm just going to quick recap last week. Last week, our first speaker was Mario, where he told us about the work that went into recovering the world's highest ice core. This expedition was part of the most comprehensive scientific assessment of Mount Everest, acquiring data relating back to biology, geology, glaciology, mapping, and meteorology. The ice core was taken from the South Col Glacier at about 8,020 meters, almost the peak of Mount Everest. Because of the hypoxic environment, Mario and his team relied on supplemental oxygen to prevent altitude sickness. And the research team, with the help of dedicated Sherpas, recovered ice cores from the Kumbo Glacier and the top of South Col Glacier, as well as multiple surface snow samples. The samples were then transported down the mountain by Sherpas, sent to Kathmandu, and eventually arrived here in Orono. The core was sampled using a continuous melting system sampling with a 1 centimeter resolution, but then in order to gain greater resolution, laser ablation sampling was used to get a resolution of 120 micrometer resolution. Results from ice cores can tell us about past climates, atmospheric circulation, and chemistry, and tell us how trace element concentration changes with time in the region. Preliminary results show us that the environmental record is preserved in this ice core, which is about 2,000 years old, and they have verified the capabilities of the Keck laser ice facility and will be able to examine sub-seasonal to storm scale signals, which is super fine resolution, so awesome job. And Mara's ultimate goal is to improve our understanding and resilience to the impacts of climate change in the Mount Everest region through comprehensive studies of the climate. And so we're excited to see what your final results are. I'll pass it on to Alessandro.
And for the second talk of last week, Wendy Azukova brought us to Greenland to explore the drivers of phytoplankton abundance under lake ice. This topic is of great relevance to understand greenhouse gases emissions, as phytoplankton is the protagonist of the carbon cycle there, and it has been proved that, contrary to prior assumption, it's pretty active under ice during the winter. And lakes tend to release carbon in the atmosphere as soon as the ice on top of the lakes melts in the spring or summer. So Wendy explained us the difference in the water column when ice covers a lake, acting kind of like an insulating layer that prevents interaction between the lake and the landscape surrounding the lake, and how this can affect the availability of the main drivers of phytoplankton abundance that are light and nutrients. To understand how seasonality and dissolved organic carbon affect the lake biomass, Wendy and her team sampled 2 lakes in West Greenland, bracketing the ice out season, so before the ice melts and after the ice melts, to measuring biotic and abiotic parameters such as like light, phytoplankton community, zooplankton community, the solvent organic carbons, and other things that tell us about the state of the lake ecosystem of the water column. Her results show a difference in the under-ice dynamics between lake with a high dissolved organic carbon and a low dissolved organic carbon, with lakes with low carbon dissolved in the water being oxygenated during the winter, while the lake with high organic carbon was anoxing until ice out. So the hypothesis that she provided to explain these differences involved the role of dissolved organic matter and water color. So that changed the availability of light when ice is covering the lake. In lakes with in lakes with high dissolved organic matter, light is blocked by the color of the water and by the presence of ice, and so photosynthesis cannot happen in the winter and resumes after the ice out. And it's boosted by the availability of nutrients that are not used during the winter. While in lakes with low dissolved organic matter, light is able to penetrate more easily under the ice and in the water, allowing growth under ice. But in this after ice out, there is not a lot of nutrients available to promote growth. So there's not a boost in growth of phytoplankton in the ice after the ice out. So this hypothesis will be tested by Wendy and her team in a future experiment aimed at disentangling the role of light and dissolved organic carbon in Greenland lakes productivity. And the goal is to understand how ice out dynamics affect phytoplankton communities and ultimately greenhouse gases emissions. And now I'll give the word to Abby that will talk about the last talk of last week.
So for our final presentation last week, it took us back to Nepal, where we heard from Suman Akaria about how rural communities of this region can benefit from renewable energy technologies when adapting to climate change. The country of Nepal is highly vulnerable to the effects of climate change, with 80% of its population still reliant on agriculture and natural resources for daily needs. Great potential exists for renewable energy technologies in Nepal. With 300 sunny days per year, Nepal has potential for significant solar power capabilities. Nepal's 6,000 river systems offer yet another option for renewable energy inputs, with the potential to account for 15% of energy demands in the country. Wind capabilities are another possibility, but are challenged due to the complications of geography, lack of roads to high mountain areas, and sparse population. Reduction in overall greenhouse gas emissions can be aided through replacement of traditional biomass fuel sources with wind and biogas, reduction in forest uses through conservation, and replacement of petroleum products by electricity derived from hydro and solar power resources. By implementing renewable energy technologies, there are many benefits to the people and communities of Nepal. These include health benefits through reduction of pollutants and malnutrition, lifestyle benefits through modernization of home utilities and appliances and the strengthening of social capital, and economic benefits possible through the use of high return renewable resources, carbon trading, energy conservation activities, and local entrepreneurship. Moving forward, Suman suggests that the opportunities and challenges of renewable energy technologies be identified within the current environmental and political climates of the country, that studies of decentralized energy systems production are incorporated, and that the potential for implementation of each of these renewable energy technologies be assessed. So on that note, I guess that we will move to our talks. Oh, actually, sorry. So the overarching theme of our talks last week was going beyond the borders and expanding our knowledge. The speakers went to cool places to push the boundaries of our knowledge on how humans and climate interactions are shaping our future. So with that, we will move to the talks for this week. Our first talk will be by Elizabeth Leclerc, and the title of her talk is Modeling Paleohydrology in the Coastal Andes to Improve Archaeological Conceptions of Water Availability.
Thanks, Abby. Let me share my screen here. There we go. Y'all can see the presentation?
Yep, we can see it.
Okay, great. A couple little housekeeping things here. All right, so today I'm presenting on research that I'm currently undertaking for my master's thesis. And the project involves developing a framework for investigating past water environments and incorporating this context into archaeological research in the coastal Andes. And I'm developing this framework through a case study of the Supe Valley in coastal Peru. So to set the stage, when we examine the impacts of modern climate change, we can see that many of these are tied to water, whether it's more frequent flooding, sea level rise, onset of drier conditions, or changes in the seasonality of rainfall. And in places where water management and land use are out of phase with local hydrology, these impacts can be particularly acute. Now, I think that archaeology has a role in helping us to trace how past societies developed water management strategies that were well suited to their particular environments and their particular social needs. And I think archaeology can help us to identify what systems were successful or not and why, how these water management systems performed or changed during periods of climate instability, and perhaps how we might use this knowledge to improve resilience today. So out to the central Andes in Peru, water has featured in coastal archaeology in two primary contexts. On the one hand, there's been a really heavy focus in irrigation technology, which has been fueled by interest in really impressive irrigation features, like the Escope Aqueduct, which is shown here on the left. Now, these studies have tended to focus on irrigation technology and the relationship of that technology to social organization. But at least until recently, there's been really little attention to hydrologic variability and how climate change might have affected water availability for these irrigation systems. And this is especially true in terms of climate in the highlands. And this is significant because the highlands provide the vast majority of water in these coastal watersheds. Now, the other area where water has featured in archaeological research is in the presence and impacts of extreme events, especially El Nino, but also in terms of drought. And these studies are definitely more environmentally focused, but they've been hampered by the lack of any kind of regional climate synthesis for the Andes, for the Andean highlands. And so while some studies have incorporated highlands records, they tend to be limited to 1 or 2 records. They might be from locations that are hundreds of kilometers away and maybe under a slightly different rainfall regime. There's also been really little attention, at least again until recently, to spatial variability and in the risk of extreme events, or the ways that extreme events manifest in particular areas. And there's been little research into how the relationship between extreme events and water management in the relationship between extreme events and water management and the resilience of water management strategies. And I think this is really an area that we should be focusing on. But to do it effectively, I think we need a way to model flow dynamics and a way to do it effectively based on the types of data that we have, which is not near as granular as the types of data used, say, in modern climatological or hydrological modeling. So what I've done is I've pulled together techniques from various kinds of modern and paleohydrological modeling studies and put this into kind of a fourfold approach that I think works for the Central Andes. It works for this environment. It works with the types of data that we have available and the types of research questions that we're interested in. So this begins with geospatial modeling, looking at watershed and channel networks, and then also deriving hydrological units. And this is a concept that I've borrowed from mathematical models used to model modern watersheds. And basically, these are units, areas with similar characteristics, and so we should expect them to respond to hydrological events in similar ways and to have similar flow dynamics. So once the geospatial modeling is complete, then there's both quantitative and qualitative analysis based on the channel networks and on the hydrological units. So the quantitative analysis really focuses on establishing surface flow conditions within these hydrological units and providing a basis for comparing these regions, again, in terms of surface flow specifically. So looking at metrics like stream density, stream order frequency, catchment area. And then the next step is a qualitative analysis. And this looks more at storage and flow dynamics within and between the hydrological units. So what kind of storages are present in terms of surface water features, groundwater reservoirs, what are the fluxes between these storages, and what's the flow direction? Not just horizontal flow between hydrological units, but also vertical flow in terms of precipitation versus evapotranspiration. And then on top of once the quantitative and qualitative analyses are complete, then we incorporate the archaeological data and site locations and radiocarbon dates and kind of overlaying settlement patterns with the hydrological patterns. So I will finally introduce you to my study area. Again, I'm looking at the Supe Valley and focusing at the time period from about 4,000 to 6,000 years ago. Now, human relationships with water have not really been at the forefront of research in this valley, but they are implied in some of the hypotheses and explanations for the settlement and abandonment of this region. So the Supe Valley and adjacent areas, these are referred to as the Norte Chico region. These areas contain some of the earliest evidence for the expansion of societies into the middle and upper reaches of the coastal valleys. And this pattern is generally thought to be associated with agricultural intensification and presumably with developments in canal technology and water management. The Norte Chico region is known for its cultural fluorescence during this period, with impressive monuments, agricultural intensification, increased social complexity. And these are perhaps best demonstrated at the site of Koettlitz, which is a 60-hectare complex that was built by 5000 BP. Now, for reasons that remain unclear, the Norte Chico region was largely depopulated around 3,800 years ago. And one explanation that's relevant to Koettlitz and was proposed by my advisor, Dan Sandweiss, and others, is that the onset of El Nino around 5,800 years ago interacted with tectonic and aeolian processes to cause sand invasion that eventually forced local abandonment. However, this hypothesis doesn't necessarily explain the widespread abandonment of the entire Norte Chico region. And it also doesn't really explain the longevity of this trend. This region remained largely unpopulated until the colonial period. So by applying my modeling framework to the Supe Valley, I hope to identify the hydrological context for these trends and to see how this compares with the existing hypotheses, and perhaps come up with new hypotheses that come out of these comparisons. So I think I'm just about out of time. No, I've got a few more minutes. So
Yeah, you're good.
I'll keep going. So the next couple slides just kind of show what I've accomplished so far. I've finished delineating the stream network and the watersheds. This was done in GIS using an Aster 30-meter digital elevation model. Now the stream, well, both the stream network and the watersheds are clearly based on modern topography. But you can kind of tell from the hillshade here that this is, at least most of this region is very heavily incised. So there hasn't been a lot of lateral movement in the streams over the time frames that I'm considering. And by and large, the stream network should reflect conditions around 5,000 years ago. Now, where this breaks down is in the middle and upper valley regions, these little pockets. Actually, I'll go back here. You can see like around Koettlitz, there's this little pocket. There's another one here. So in these areas and in the coastline, the coastal plain, there's definitely been more lateral movement. And I just don't have the data available to be able to trace that. There hasn't been much work on geomorphological analysis or dating of landforms in this area. So that's something I'm really just going to have to keep in mind as I move forward. Now, I'm currently working on delineating the hydrological units, and this is through an overlay analysis, again in GIS, using several variables. So I'm looking at slope, which is again derived from the digital elevation model. I've digitized geology from geological maps of the region. I also have soils data, and I'm currently working on developing the climate layer. So this is kind of a provisional delineation of climate zones. And actually the climate zones has been one of the more challenging aspects of this, because as I mentioned, there is no regional synthesis. And so I had to put this together. I've looked at over 20 different studies from areas that are relevant to establishing the Norte Chico paleoclimate. And I'm showing, all of them are here except for one that kind of falls off the screen. And these can be broken down into 4 categories. These tend to look at proxies for atmospheric circulation or intensity of the South American summer monsoon. Some look at moisture balance and lake levels. Others look at glacier mass balance, and then also proxies for the El Nino Southern Oscillation. And so another challenge is that the climate here between the coast and the highlands is very different. These areas are controlled by very different climate mechanisms, and there's also virtually no information on the boundary between these zones. So the climate zonation for the hydrological units really requires some assumptions about the climate patterns based on modern studies, and then also the paleoclimate synthesis. So that's where I stand now. My next steps is to finish modeling the hydrological units, and then kind of working through that, that approach I laid out earlier, doing the quantitative analysis, incorporating qualitative analysis of flow dynamics, and the archaeological data. And then I also am looking further on after completing my master's thesis, and I want to carry this forward into my doctoral research, looking at another valley and doing more of a comparative analysis, and hopefully digging more into the social aspects of these questions and these relationships with the hydrology. So this research is supported by the National Science Foundation Graduate Research Fellowship Program and also the UMaine Graduate Student Government and provisional funding from the Churchill Exploration Fund if I get to do any fieldwork. And I didn't describe the fieldwork, but it would involve some ground truthing of the geospatial modeling and characterization of the modern hydrology. Special thanks to my committee, Dan Sandweiss, Charlene Jane, Kirk Mosh, and Alice Kelly. And also thanks to Tora Johnson at UMaine Machias, who's been helping me with some of the geospatial modeling. And with that, I can take any questions.
Yeah, thank you very much, Elizabeth. We'll open it up to the group for questions.
Yeah. I have a question regarding the groundwater regime. And that is, do you have any idea how deep those valleys are at the lower ends of the drainage system and what they're made of? Are they tight clays? Are they porous sediment, sands, or anything of that sort?
Yeah, there's not a lot of data on the soils and the depth of the valley for the Supe Valley specifically, and so I'm going to have to broaden that out a little bit and maybe make some assumptions on that. I know in some areas, some of those sediments in the lower in the coastal plain can be more than 4 or 5 meters thick, and they I do think they tend to be more coarser grained sediments, sands. And silts, not so much clays, I don't believe, but I'll need to dig into that aspect a little more still.
Yeah, thank you.
Yeah.
I had a question. First of all, that was an amazing pun, Elizabeth, digging into the sediments. But I was wondering if you could just give us a little bit more detail about this climate map that you're making. You're putting an enormous amount of effort into it. That's really incredible. And just like, what is your end goal with that layer and how are you combining it with the other layers in this research?
Sure, yeah, let me go back to that slide here. So I'm after looking at the modern climate data in the paleoclimate records, my approach is I'm thinking 4 different climate zones here, basically dividing broadly between the coastal regime and the highlands regime. And then within that, looking for things that are going to affect hydrology, like snowline and the equilibrium line for glaciers, because the glacier accumulation is going to play a big role in water storage and the seasonality of flow during periods of glaciation. Now, it's still kind of a question whether there were glaciers present in this watershed during the time frame I'm looking at, but it is within the realm of possibility. So I'm actually probably going to come up with a couple of different climate scenarios and then kind of carry those through the analysis. And then I'm also kind of this dark gray shading you can see down in the coastal region. This reflects lomas, which are these fog, precipitation, vegetation zones. And so trying to model where that precipitation happened. And I'd like to, basically I'm trying to create a model like this one shown here in GIS so that you basically plug in the elevation that you want for the snow line and then an elevation for like the ceiling of the fog zone. And you would do that based on the paleoclimate synthesis. Does that answer your question?
Yeah, it does. This is just such an incredible, it's a really interesting approach. So thanks for your answer.
Yeah.
Are there any other questions quickly for Elizabeth? If not, we will move on to our second talk. Thank you very much, Elizabeth.
Yeah, thank you.
Yeah. So our second talk today will be by Ann Hill, and the title of the talk is Surface Changes Across the McMurdo Ice Shelf, Antarctica. Okay, I think we see it.
Okay, so I'm Ann Hill, and for my talk, I'm going to be talking about quantifying the surface elevation change on the McMurdo Ice Shelf in Antarctica. So here's a map of my study site, the McMurdo Ice Shelf, and you can see the areas in the red boxes are my preliminary study sites. These are the terminus area of Koettlitz Glacier, which is shown in the larger box, while the Hut Point region is shown in the smaller box. And the McMurdo Ice Shelf borders the northwest corner of Ross Ice Shelf, and the approximate ice flow direction is indicated by the black dashed arrows. So ice shelves form when glaciers flow off their bed and float on the ocean. And the ocean must be cold enough so that the ice doesn't melt immediately. And ice shelves act as a buffer to their tributary glaciers by slowing their flow and reducing the rate of mass transfer from land to sea. In the absence of ice shelves or following their disintegration, glaciers can accelerate and drain mass rapidly. While glacier contribution may help to thicken and stabilize ice shelves, ultimately glacier ice is limited, and once the ice flows from the tributary glaciers across the grounding line onto the ice shelf, that mass contributes to sea level rise. And you can see in this diagram, in the top frame, there is a glacier with a full ice shelf, and that ice shelf and the ocean together act as resisting forces against the driving force of the glacier. And those resisting forces restrict the flow of the glacier, causing a slower glacier velocity. And then the next frame, part of the ice shelf has disintegrated, resulting in the resisting forces acting on the glacier being reduced, and therefore the glacier velocity increases. And then when the ice shelf is completely gone, the ocean provides the only resisting force to the glacier, and the velocity increases more. And then in the bottom, on McMurdo Ice Shelf, thinning is largely due to subglacial melt from warm water circulation, as well as unusually high surface melt. So here's a diagram of ocean circulation under McMurdo Ice Shelf and Ross Ice Shelf. And Ross Ice Shelf is a majority of what you're seeing in the kind of the white area. And McMurdo Ice Shelf lies within the black circle, and that's in sort of the bottom right-hand quadrant of the diagram. And East and West Antarctica both drain into Ross Ice Shelf, which is buttressed by McMurdo Ice Shelf. And McMurdo Ice Shelf is more vulnerable to collapse than Ross Ice Shelf because it is a lot thinner, and the surface melt, the summer melt rate on McMurdo Ice Shelf can reach as high as 10 meters per year, while the summer melt on Ross Ice Shelf only reaches about 2 meters per year at the most for most of the area. And McMurdo Ice Shelf also has a summer melt rate that covers, the surface melt covers approximately 25% of the area. And in addition to buttressing the Ross Ice Shelf, the stability of McMurdo Ice Shelf is critical to the US and New Zealand logistics for their Antarctic programs. And on the next slide, you will see a cross-sectional view along transect E, which in this diagram is the dotted line that crosses through the black circle and over McMurdo Ice Shelf. So here's a diagram of sort of the ocean circulation specifically in the region that I'm interested in. And again, McMurdo Ice Shelf is in the black circle, and the AASW is the Antarctic surface water, ISW is the ice shelf water, HSSW is high salinity shelf water, and MCDW is the modified circumpolar deep water. And as you can see, McMurdo Ice Shelf is most susceptible to the Antarctic surface water, and this is the warmest of these currents, and it consequently lies in the uppermost portion of the water column. And given how thin the McMurdo Ice Shelf is in comparison to the Ross Ice Shelf, the Antarctic surface water can flow under the McMurdo Ice Shelf and cause melting, but it does not reach under to the Ross Ice Shelf. So my overarching question for my thesis is, what is the relationship between changes on the surface of McMurdo Ice Shelf and the behavior of its tributary glaciers? But for this talk, I'm going to specifically be focusing on preliminary results of changes in the surface elevation at these two sites, the Terminus area of Koettlitz Glacier and the Hut Point region on McMurdo Ice Shelf. So in order to do this, what I'm trying to get at is really the change in the thickness of the McMurdo Ice Shelf. And I do that by differencing digital elevation models, or DEMs. And first, these need to be grounded and corrected for tides and atmospheric influences. So to ground truth the DEMs, I compared IceSat2 tracks to the elevation values of the DEMs, and then adjusted the DEMs to match the elevation of the IceSat2 data. And I then used a model to produce the tidal height across the study area at the time that the DEM was created. And then I removed that tidal signal from the DEM. And finally, I used in situ sea surface pressure data to remove that signal from the DEM as well. And then I was able to difference these corrected DEMs to arrive at the change in the ice shelf thickness over time. So here are my preliminary results for the change in the thickness between February 6, 2011 and November 25th, 2015 in the Hut Point region, with thinning along the ice shelf front and variable elevation change across Hut Point. The shelf front thinned by approximately 1 to 4 meters, and the spatial extent of this thinning aligns well with the retreat of the ice shelf front between these two dates. And you can see in the diagram, the two purple dashed lines indicate those ice shelf fronts at that date, at those dates. And on the east side of Hut Point, which in this figure is on the left side of the figure, the elevation decreased by about 2 meters, while the elevation on the west side increased by about 4 meters. And both of these changes align with previous findings. The orientation of the ice folds in that ice fold region led me, you can see that it aligns with the direction of the ice flow. And the elevation changes seen in this area could be caused by either ablation and accumulation, or more likely by shifting of those peaks and the troughs of that folded ice as the ice moves. And additionally, the 2011 DEM was collected in mid-summer, while the 2015 DEM was collected in late spring. And that could attribute some of the elevation change seen to changes in the snowpack. These results also led me to some questions, including what accounts for the largest elevation increases and decreases seen on land. And is that perhaps from differences in snowdrifts, or could that be from something else? And why does the location of the ice shelf front on February 6, 2011 align so well with the boundary between elevation gain and loss, except for in this middle region right here, where it kind of deviates from that distinct boundary? And here are the results of the changes in the thickness in the Terminus region of Koettlitz Glacier across December 26, 2010, December 19th, 2011, and November 5th, 2016. So in pane A, between 2010 and 2011, there's consistent thinning on the ice shelf ranging from roughly 0 to 3 meters, while in pane B, between 2011 and 2016, that shows almost entirely ice shelf thickening from approximately 1 to 3.5 meters, but the land shows elevation increase. And in differencing the 2010 and 2016 data in pane C, we find variable change in the thickness. And the signal of ice shelf thinning seen in the 2010 to 2011 differencing could be present in that variable change seen from 2010 to 2016, but it would not be present in the 2011 to 2016 changes. And also the 2016 DEM was collected over a month earlier from the 2010 and the 2011 DEMs. And so therefore the presence of additional snow in 2016 could account for the increase, or at least some of that increase that we see in pane B. And also in the middle region of pane C, you can see it has that same kind of folded ice pattern that we saw at Hot Point, with a lot of variable surface changes across this area. But why isn't this pattern as prevalent in both panes A and B? And these preliminary results indicate the importance of looking at changes between multiple years instead of just looking at the average between two end member dates. So for some next steps, I would like to investigate other facets of surface change on the McMurdo ice shelf by quantifying changes both spatially and temporally with regard to glacier surface melt as well as glacier surface velocity. And I'd also like to investigate the shifts in the grounding line of McMurdo ice shelf tributary glaciers to gain further understanding of the relationship between changes in the ice shelf and its tributary glaciers. Thank you, and I will take any questions.
Thanks, Anne. I have a question for you regarding the continuity of the in 3 dimensions and whether you can remove some of those folds by looking at the 3D fold information or flow information that you have once you get your velocity field.
Yeah, right here.
Yeah, right. Right. So in other words, once that's in, yeah, you should be able to solve for continuity for the full mass and remove some of that fold noise, or else use the fold noise to learn more about it.
From the velocity data.
Yeah, right.
Yeah. Okay, cool. Thank you.
And strain rates from that.
Okay, cool. Thanks.
Yeah.
Yeah, I had a question. What is the ICs at 2 tracks? Could you explain that a little bit?
Oh, yeah. Here where I talk about the ice at 2 tracks.
Yeah.
Yeah, so it's these elevation profiles that were taken by satellite, and it's basically like something that we're gonna compare the digital elevation models to. And so we're gonna kind of correct all of the digital elevation model data to these other like sort of fixed points that we know, because we know those elevation data really well, and those are much more accurate. So we're going to kind of scale everything to that so that we can compare. We have kind of this common thing that everything is compared to, and then we can compare across all the different digital elevation models.
Thank you.
If there aren't any other questions for Anne, we can move on to our third and final talk today. Thank you, Anne. That was great. So our third and final talk today is by Aaron Chesler, and it's titled Decoupled Acid Reactive and biologically relevant iron concentrations during termination 1 in the South Pole ice core.
All right, thank you, Abby.
Uh-oh, Aaron, I don't know if we can hear you.
How about now?
Up a little bit?
How about now?
Perfect.
All right. All right. My computer is always funky. All right. Thank you, Abby. Can everyone see my slideshow and not my notes while that whole process happened?
Yes,
Okay.
looks good.
Great. Thank you. I'm excited to present new ice core data that bears on atmosphere-ocean carbon cycling during the last termination. These are novel new measurements and a step forward in interdisciplinary ice core analyses of Earth systems relationships on glacial interglacial cycles. And what I'll be particularly focusing in on during this presentation are microparticles and their geochemistry. Microparticles are micron-sized pieces of rock, or dust as I'll be referring to throughout the rest of this presentation, that are transported to Antarctica, either from Antarctica itself or from mid-latitudinal sources, and then get deposited on the continent. And dust that's transported from the mid-latitudinal sources, such as South America, like I've included an image of on the right, some of that dust during transport falls out over the Southern Ocean. Now, the Southern Ocean is limited by how much, the amount of iron that's available to be used by phytoplankton populations. And so the amount of iron controls the size of these populations, depending on how much iron there is. Now, when more dust is transported up into the atmosphere, more dust falls out, and that dust contains iron. So when there's more dust in the atmosphere, there's more dust that falls out. The dust increases the ambient concentrations of iron in the Southern Ocean, and that allows for phytoplankton populations to bloom. And in 1990, Martin used this relationship or this coupling between dust, iron, and phytoplankton to create the iron hypothesis. And the iron hypothesis is really just using this relationship, but extending it back until the last glacial maximum, where CO2 concentrations were about 80 parts per million lower than early Holocene values. And I've included an image of this on the right. So in black are dust particles from the South Pole ice core and concentration of particles per milliliter. And then in green is the waste divide CO2 record going back between 10 to 20,000 years ago. And so Martin hypothesized that the change in CO2 was partially due to increased amounts of dust in the atmosphere, bringing iron to the phytoplankton in the Southern Ocean and allowing for increased phytoplankton population blooms, leading to increased photosynthesis, which led to a transfer of atmospheric CO2 in the ocean via the biological pump. And this has led to the next 30 years up until today in 2020 of iron research in Antarctica. And so I've included, now on top, I've also included the South Pole iron concentrations in red, and in blue is the waste divide delta 018 values, which is just a proxy for temperature. And so iron and dust are correlated well with each other, as you can see in the plot on the right. And they have a significant anti-correlating relationship to CO2 and temperature proxies. So when iron and dust are high, CO2 and temperature are generally lower. Now, the problem is that most of these iron concentrations in Antarctica have been measured at what we're calling the acid reactive fraction of iron, which is around pH 1, maybe ranging, about pH 1. And oceanographers have defined biologically relevant iron, or iron that's available to phytoplankton, as pH 4.2 to 5. And so all these iron measurements have overestimated what the iron is that's available to phytoplankton. And so these iron measurements that have been done are either done in a single fraction, so this acid reactive fraction, and if they did measure biologically relevant iron, they're not continuous measurements, and they've only spanned maybe either during the modern day or from 21 to 26,000 years ago. And all of the conclusions that are interpretations from iron in Antarctica have largely been made with this assumption that acid reactive iron, the iron taken at pH 1 values under really acidic conditions, is equal to biologically relevant iron. And so we ask the question, does acid reactive iron equal biologically relevant iron concentrations? And so we use the South Pole Ice Core microparticle record in their trace element geochemistry to answer this question and shed some light on how does the biological fraction relate to the acid reactive fraction. And so this is a short, quick diagram of all the measurements that we've made over the past 4 years on the South Pole Ice Core, and split into two sections. There's the microparticles, where we made continuous abacus measurements, which counts the particles at very high resolution. We've had discrete measurements of Coulter counter samples, which measures accurate particle volume. And then we've made some novel flow cytometry measurements using Jacqueline Gill's flow cytometer to measure particle aspect ratio, so measuring particle shape. And at the same time, we've also made trace element geochemistry measurements in a high resolution continuous fraction and a low resolution discrete fraction. And these fractions, and for the high resolution, we've done our acid reactive fraction, our biologically relevant fraction, and our dissolved fraction. And then for the low resolution, we've done those three again, but adding in this total, which we used hydrofluoric nitric acid for digesting the particles entirely to get a total concentration. And so this is the first time we can assess high resolution fractional chemistry in comparison with particle shape, size, and volumes. And so what I'm showing here is just our trace element methods. We use continuous flow analysis, or CFA, where we melt the ice and obtain particle concentrations through the abacus, but also collect bulk samples, which we later split into these 4 fractions. We got about 10 to 14 milliliters per sample, and then we broke them down into the total fraction, where we used hydrofluoric nitric digestion, our acid reactive fraction, where we acidified the samples to just below pH 1, and then we created our biologically relevant fraction, where we used ammonia acetate buffer to buffer the samples to pH 5, so right between the oceanographic defined values biologically relevant. We also did a dissolve fraction where we filtered the sample before acidifying, but I'm not showing those today. And so we present 2 sets of trace element data. One, this high resolution and continuous data for the acid reactive and the biologically relevant fraction from the modern day to 16,000 years ago, and then our low resolution and discrete samples for the total fraction, acid reactive, and biologically relevant fractions from 10 to 50,000 years ago. And so here is our compiled South Pole iron record during the termination Holocene, and then some discrete samples extending back into about 50,000 years ago. And so at first order, things are stratigraphically where they should be, or hierarchically where they should be, with the total concentrations at the highest values, then our acid reactive, and then our biologically relevant fractions, and they all increase moving into the last glacial maximum about 20,000 years ago. So we compare our acid reactive, which is fraction, to other Antarctic sites, because this is the most comparable fraction that we have. And so what I've plotted here is the median iron flux at each site for the Holocene by its elevation, and included a geographical map of each site and where they're located in Antarctica. And what I'd like to point out with the main point of this image is that the spice core iron flux values are similar to other sites with comparable elevation. So Epicadrone Maudlin, that's EDML, that's located in the Atlantic sector, just below 0 degrees on the map, and to sites with regional atmospheric patterns. So that would be Epicadome C, or EDC, and that's located in the East Antarctic Plateau. So now that we've done this, we can ask the question, and we can see that the South Pole iron records are comparable to other anticites is what is the temporal relationship between the continuous fractional iron concentrations. So I created the fractional iron ratio. So I took the ratio of acid reactive iron to biologically relevant iron and then resampled that to 200 years and compared that with particle concentration and the particle mode size. And the mode size on the bottom in red is just basically saying if the mode value is larger, the particles are larger or coarser, and if the mode value is smaller, the particles are smaller in size or finer. And so we compared the ratio between these two microparticle properties or physical properties. In the fractional iron ratio has a much more significant relationship to particle size than it does to particle concentration. Particle size has been previously hypothesized to be reflecting or affected by the strength of the southern hemisphere westerly winds. And I'll break this down a little bit further, is that when the fractional iron ratio increases, or we have relatively more acid reactive iron, we're seeing finer particles. And when there's more biologically relevant iron, we see coarser particles. And so we create this hypothesis around this, that the amount of biologically relevant iron is dependent upon the dust source region because particle size is affected by transport. And so coupled changes in dust size and geochemistry are related to southern hemisphere westerly wind strength. We're hypothesizing that fine particles transported from the mid-latitudes have an increased amount, a relatively increased amount of acid reactive iron, and coarse particles being transported from Antarctica have an increased biologically relevant fraction. And this change could be related to activation, deactivation of Antarctic dust sources or mineralogy. But we extend this question a little bit further and we use our total concentration and say, how does the proportional relationship of acid reactive and biologically relevant iron compare to the total concentration? And so I'd just like to point out, these are raw data I plot on here. They just made this just worked through this in the past week. But what I've plotted here is iron recovery rates. And it's basically just a percentage of one fraction compared to the total. So in blue, I have the acid, plotting up here, the acid reactive relative to the total as a percentage. And then in red is the biologically relevant fraction compared to the total as a percentage. And then in the gray in the background is the waste divide delta 018 temperature proxy record for the past 70,000 years. And there are two major conclusions that we can draw from this, is that the acid reactive, the recovery rates or the proportion of acid reactive iron throughout from 10 to about 50,000 years ago has remained relatively stable, ranging from maybe 5 to 20%. Whereas the biologically relevant fraction tends to fluctuate with climate. So there's two conclusions from here. One, fractional iron relationships are not constant. And two, the proportion of biologically relevant iron appears to fluctuate with climate. And so to conclude here and move forward with our next steps, changes in acid reactive iron does not equal changes in biologically relevant iron. In that the measurement, and we need to include in Antarctic iron research studies, we need to include this biologically relevant fraction. Proportionally to the total fraction, acid reactive and biologically relevant iron are also affected by different processes. And changes in the biologically relevant iron seem to be affected by particle transport or particle size. And this could be a factor of dust mineralogy. This is something that we're looking into in the future as our next studies. With that, I'd like to say thank you to my advisors and to my committee, University of Maine Grad School, as well as the students in the department, and Dartmouth, Dartmouth College, South Dakota State, and Colby as well. Thank you.
Thank you very much, Aaron. So I will open it up for questions. We have just a few minutes left.
Yeah, I have a question. Could you just describe again what exactly acid reactive iron is?
Yes, acid reactive iron is just iron that's so all the iron that's been acid reactive iron has been acidified to about pH 1. There have been studies in the past. There have been several studies in the past that have shown that if you use nitric acid or hydrochloric acid, which is a moderate acid in the grand scheme of things, if you use one of those acids, you get a certain fraction of iron. You don't get all of it. To do that, you need to use hydrofluoric acid in combination with nitric acid to get the total concentration and to break down the silica bonds in the mineralogy of this dust. So it's called acid reactive because it gets a proportion of the total amount of iron.
Okay, thanks.
Yep.
Well, if there are no more questions, I'll make a few closing remarks and we'll close today's session. So Elizabeth Leclerc spoke about a new approach to understanding prehistoric water management systems. She isn't exactly claiming that prior approaches are all wet, but she wants to float a new idea about how to study these systems. She calls on us to connect the highland sources of coastal streams to coastal outcomes. In other words, we must remember that top to bottom, a river runs through it. If we want to understand the systems, we have to go with the flow. In fact, she provides a flow chart on how to connect quantitative and qualitative data on hydrology to social systems and management practices from archaeology. And then she channeled the discussion into a summary of the data that she is pooling for this study. And he'll discuss the ups and downs of the McMurdo ice shelf. She offered a fast outline of the dynamics of glacial velocity and then gave us the skinny on thinning of McMurdo. Like Elizabeth's talk, the key to Anne's work is going with the flow of water masses and of ice. As Anne accumulates more data, a clearer picture will surely emerge. Finally, Aaron Chesler's core questions have to do with climate dynamics in glacial and interglacial periods. He is studying the dust of the ages to assess the iron hypothesis. It takes a lot of metal to attach such a big picture question. It turns out that previous measurements of iron feeding phytoplankton were not in fact ironclad, and Aaron had some acid remarks on that earlier work and described particular methods to do it better. This fine approach could change the course of our understanding of iron's role in phytoplankton blooms through time. Thank you all and see you in a week.